Section 9-6 is on integration by trig substitution. The objective is to simplify the integral of a function containing the square root of a binomial using trig substitution and then integrate. All right, so let's take a look at one more example of trig substitution. This one involves actually a definite integral. It says find the area of the zone of the circle x squared plus y squared equals 25 between x equals -2 and x equals 3. All right, so let's write down the equation they gave us here. First of all, it's x squared plus y squared equals 25. In fact, I'm going to write it as 25, or that's 5 squared, remember, so that's the radius of this circle. In fact, I'm going to go ahead and sketch what this looks like here. This is the equation of a circle centered at the origin, and it has a radius of 5, so this is 5 and -5 on the x-axis and 5 and -5 on the y-axis. But they said to find the area of the region from x equals -2 to 3. So we'll say that this is -2 about right here, and we'll say that this is about 3 right here. So they're asking us to find that region in between those. All right. So to do that, we've got a couple of things that we've got to do here. First of all, I'm going to draw a vertical strip in here from the top curve to the bottom curve here of this circle. And I'm going to label the top curve here. We'll name this x y2. And this will be x y1. So we're just finding the area between those two curves there that make up this circle. And if I find the area of that one strip, I will be able to use integration to find the area of the whole region. So we say that dA is equal to, it's just the base times the height here for this thing. In fact, I can write it that way, base times the height for that rectangle. So the base of this, actually let me deal with the height first of it here. The height of this thing is the difference of those y values there, y2 minus y1. And the height, or excuse me, the base of this is the thickness of this. And the thickness of this, that's this distance right here, is a small change in x. We call that the dx. So that's times dx. All right, so y2 minus y1. Now y2 is on the top curve there, but so I need an equation for that. But they didn't give me an equation here. They gave me the equation of x squared plus y squared equals 25. I should say they didn't give me the equation solved for y. So let's solve that thing for y. If you have x squared plus y squared is equal to 25, and let's move the x squared to the other side, y squared is equal to 25 minus x squared. And now take the square root of both sides. Of course, when we do that, we'll get a plus or minus the square root of 25 minus x squared. Now the plus is the top half of the circle, the minus is the bottom half of the circle. So for us, we have dA is equal to, y2 was on the top part of the circle, so that's the positive square root of 25 minus x squared. And the minus, y1 was on the bottom part of the circle, that's the negative square root of 25 minus x squared. And that's all times dx. Let's draw a line there so we can separate those. All right. So this actually becomes, because of the fact that you've got the square root minus that, or minus a negative square root, becomes 2 of those guys, and that turns out to be addition. So it's 2 square roots of 25 minus x squared times dx. And you could have, if you would have, instead of going from the top curve to the bottom curve, you could have gone from the top part of this circle to the x-axis and just found the area of this strip. And of course that's only half the area, so you could have doubled it, and guess what, we would have gotten this thing right here as well. So you could set it up either way. And now to solve this, we integrate both sides. The integral of dA is equal to the integral of 2 times the square root of 25 minus x squared dx. And we have to have limits of integration. We're going from x equals -2 to x equals 3. That was the limits they gave us there in the problem. They said to integrate from, or find the area from -2 to 3. Now, even though this is a circle, we don't have a nice formula that we can use to find the area of the region they're describing. This is where calculus is needed. All right, so on the right side there, you can see that we have the integral of a square root of 25 minus x squared. This looks like one of those triangle problems that we've been working with. So the way to integrate this, we're going to use fundamental theorem to do this, is to use a trig substitution. So let's draw ourselves a triangle that has 25 minus x squared as one of the sides of that triangle. Let me just draw this down below. So we've got, here's our triangle. And the square root of 25 minus x squared, so that means that I'm going to put the 5 as the hypotenuse. It's the square root of 25 there. So the first part there is the hypotenuse. This guy right here, since it's subtraction, tells me this is the hypotenuse. Those two pieces of information tell me that. All right, and then the vertical leg there, I'm going to make x, and the horizontal leg is the square root of 25 minus x squared. Again, our choice here is to make the vertical leg x every time if we can. But if it turns out that x is on the hypotenuse, then we put the radical on the vertical leg. All right, so now let's find out what the radical is equal to. If I use the adjacent side and the hypotenuse, that looks like cosine. The cosine of theta would be equal to the square root of 25 minus x squared divided by 5. And so 5 cosine of theta is equal to the square root of 25 minus x squared. So again, we now have a substitution for this part right here. We still need a substitution for dx. So now, using the opposite side, the x and the hypotenuse, the 5, we would have that the sine of theta is equal to x over 5. So that means 5 sine of theta is equal to x. And so taking the differential of both sides, we would have 5, derivative of sine is cosine of theta d theta is equal to dx. All right, so now I have a substitution for the dx part right here. All right, so now let's do our substitution in this problem. So we have the integral of dA, which of course just turns out to be a, so I'll write that down. And that's equal to the integral of, the 2 is still there in the problem. I'll go ahead and put that in the radical there, or in the integral there. You could pull that outside of the integral if you wanted to. And then it's the square root of 25 minus x squared, which we said was 5 cosine of theta. And then for the dx we said was equal to 5 cosine of theta d theta. Okay. And now for the limits of integration, we've now changed this over to theta. Anytime we do a variable substitution, we went from x's to theta now, we have to also do a change of our limits here as well. Get it in terms of theta. So to help us do that, I'm going to take this equation right here that involves the simpler form. You can see this one here has a square root of 25 minus x squared. This one here has an x in it. So I'm going to use this second form here and solve that for theta. You don't necessarily have to rewrite it, but I'm going to go ahead and do so. That theta would equal the sine inverse of x over 5. So I'll replace x's with theta values now. So the lower bound was x equals negative 2 in the original. So if I substitute in for x is negative 2, I'll get theta as the sine inverse of a negative 2 over 5. And the upper bound, that was x equals 3, so it's going to be the sine inverse of 3 over 5. It'd be nice if those were nice numbers to write down or even to work with. They're not, so I'm just going to leave them in that form, but nonetheless, that's our lower and upper bound. All right, so let's rewrite this before we use fundamental theorem on this to evaluate it. I've got 2 times 5 times 5. That's going to be a total of 50. I'll pull that out front. And I've got the cosine squared of theta, because it's cosine times cosine. And that's still being integrated from sine inverse of a negative 2/5 to sine inverse of a positive 3/5. So I have the integral of cosine squared. So I have a power of a trig function. I got to go back a couple of sections to recall that I know how to integrate powers of trig functions. These were the topic of section 9.4. These are the reduction formulas. So I can use my reduction formula to be able to evaluate this. So again, you got to recall what your reduction formula is in order to use it, but we're ready to use it here. The 50 stays out front, and now I'm going to multiply that 50, of course, all the way through here. And we have cosine squared. So cosine squared, n is equal to 2, in other words, is equal to 1 divided by 2 times the cosine of theta, sine of theta, and then plus 1/2 the integral of cosine to the 0 of theta d theta. And we're going to evaluate this. I'm just going to use our vertical line to indicate that we're going to evaluate this from our lower bound of sine inverse of a -3. I'm sorry, that's not a -3. It's a -2/5 to the sine inverse of a +3/5. Okay. So let's distribute the 50 through there and actually integrate that last part there as well. So we end up with 50 times 1/2 is 25 cosine of theta, sine of theta, plus 50 times the 1/2 is going to be 25. Now again, cosine to the 0, anything to the 0 power is 1, so you have 1 d theta. The integral of 1 is just your variable. It's just theta, so it's 25 theta. And we're going to evaluate that from the sine inverse of a -2/5 to the sine inverse of a +3/5. This will be our way to evaluate that. And to do this, you could, of course, just plug those in right now and write down what you get. I like using my calculator here at the end, at least, to help me out. And if you take and punch in y1 is that function we're working with, it's the 25, the antiderivative, I should say. It's 25 sine of, or they have cosine first, so I'll do it that way. Cosine of x, sine of x, and then plus 25 times x. And I'm just going to tell it to take y1 and plug in the upper bound, which is the sine inverse of 3/5, and subtract y1 evaluated at the sine inverse of a -2/5. Make sure you're in the right mode here, of course, so you get the correct answer when we're done. And we get 47.541. And that is our definite integral. That is the area of this circle. It's not really a quarter or a sector of a circle. We've taken a circle and chopped off, the left and right part of that circle, and we ended up with this definite integral. All right. The key there, just remember that anytime you involve a definite integral and you're doing any type of substitution of variables, you always have to change those variables over to whatever variable you're switching to. So the original values were from x equals -2 to x equals 3. We have to switch those over to theta values. All right, and that's as far as we're going here with this second half of this section.